You are doing well. My name is Shriya Bansal, and today we are going to talk about a new problem based on sorting algorithms. Very specifically, here we are going to talk about quicksort. So first we'll figure out an optimized way to solve the problem after looking at the problem statement, and then we will implement our logic to verify whether our approach was correct or not. So let's take a look at the problem statement first. So the problem says that you're given an array A and you need to sort it without using any extra space and also keeping the ordering of the similar elements same as that of the original array, and you need to do this in a time complexity of n log n. So you can simply see in the input you're given an unsorted array and then you need to sort it, right? Nothing too new over here. The elements are 5, 3, 7, 2, 6, 9, and here the output is simply the sorted arrangement of the elements. So you can see clearly over here, the question just asks you to implement quicksort. Okay, here I'm sure you must have already taken the class where we solved quicksort, right? If not, I would recommend to watch that class first, right? And then come over here to solve this question, all right? But in its essence, the question simply expects you to apply quicksort on an unsorted array. Okay, so I'm sure you have already done quicksort, so we'll just directly move on to the implementation for this problem after taking a quick recap on what exactly quicksort is and what is the heart of quicksort as a sorting algorithm. All right, so let me take input array, right, which will give you a good example on how this concept works. So let's say we have an array element 7, -2, 4, 1, 6, 5, 0, -4 and 2. So as you already know that in quicksort, the heart of the algorithm is the concept of partitioning, where we pick any random element of the array which we've already decided either it can be the first element of the array or the last element of the array or some middle element. We pick that element, consider it to be a pivot element, right, and arrange all the other elements of the array with respect to that element. Okay, and that concept is known as the concept of partitioning. So let's look at an example for that as well. So let's say I always pick the last element of my array as the pivot element. Okay, now based on that, what will happen is here 2 will be my pivot element. So I will partition the entire array in such a way that all the elements less than 2 will come over here and all the elements greater than or equal to 2 will come over here, and obviously maintaining the ordering of the elements. So I'll start with the start. 7 over here, okay, 7 over here, -2 over here, 4 over here, 1 over here, 6 over here, 5 over here, 0 over here, -4 over here, right? So as you can see, we have divided the entire array into two parts, right? And definitely the right position of 2 is between these two partitions, correct? So that's what happens over here. You partition the array in such a way that all the elements smaller than the pivot element are on the left side and all the elements greater than the pivot element are on the right side. Okay, and when you do that, when you do this kind of pivoting in the array, as a result 2 come at its right position. Okay, now the elements on the left side are still not at the right position. The elements on the right side are also still not at the right position, right? But when you consider both of them, right, you can say that because of this kind of partitioning, 2 came at its right position, right? And that's what the concept of quicksort is. And then we keep on doing this process recursively. So next time for the 2 partition, -4 will be the pivot element. So hence all the elements less than -4 will go here and all the elements greater than or equal to -4 will come over here. So what you will see is that in this case we will have -1, -2, 1 and 0 because all elements are greater. So this is basically empty and -4 comes over here. Similarly, when you do that for the right hand side partition as well, 5 is the pivot element. So all the elements less than 5 over here, all the elements greater than 5 over here. So here in the elements less than 5 is 4 and then we have 7 and 6. Remember that we are maintaining ordering of the elements. Here if 7 came earlier, right, and 4 came or 6 came later, so in the output also here it is following the same ordering. And this process you keep on doing till the time there is only one element in every partition. So this is 5 in between them. So when you do for this, right, again less than 0 on one side, greater than or equal 0, or here. So less than 0 is -2, greater than 0 is 1, and the 0 comes in here. Similarly, this is only one element for this partition. 6 is the pivot element. So all the elements less than 6 over here, all the elements greater than or equal to 6 over here. Less than 6, nothing. Greater than 6, 7, and 6 in here. So now you can see each and every partition just has one element. Correct? And that is when we can say that all the elements are actually at their right position as well. And that is what exactly the concept of quicksort as an algorithm is. Okay, so this is how we are going to take our approach at this question, right? We are going to do the partitioning concept again and again, right? And then we are going to solve this. So first, let's just implement the recursive implementation part, okay? Because I think that part is absolutely clear to all of us. And then we will take a deeper dive on how the concept of partitioning can be implemented. So we have not really looked at the implementation perspective of that. So we'll have a function quicksort. In it we'll pass the array. We'll also pass the first index of the array, like 0 over here, and also the last index which we are considering. So this will help us to virtually take some part of the array. Okay. Now so this is nothing but a recursion question, and all recursion question always have three things, if you remember, right? If it's a question based on recursion, it will always have a base case. It will always involve some self work, and it will always include a recursion call as well. Okay, so the moment we are doing the partitioning, right, or the quicksort method, start is here and end is here, right? And when we will move these pointers, at some point start will be greater than end, and that's when we stop. So we simply return. Okay, then we simply call the partition function. Okay, and in that we pass the array which is under consideration, and this function basically returns us the index where the partitioning element is present. Okay, and how is that useful? Because what we will do is then we will call quicksort recursively on one part, which is starting from start to index -1, and the other part from index +1 to end. Okay, now let me help you through how this is working. So when you start, this is where your start index is, right? And this is where your end index is, correct? After you do this entire partitioning process, right? After you do this partitioning process, what will happen is start will still be here, end will still be here, and the pivot element is actually at this position. So in turn, what is happening is after we did this partitioning now, the array got converted to this. Okay, so like I said, the start remained here, the end remained here, and this is the index of the pivot element. So when we do it recursively, this is the left part which needs to be done, and this is the right part, and that is what we have written as well over here. Okay, now the only thing that we need to implement is this partition function, okay, which takes the array, which takes the start, and which takes the end. Okay, now let's see for that as well. Let me give you an example how this partitioning is working. So let's take the input array again. So we have 7 minus 2, 4, 1, 6, 5, 0, 4 minus 4 and 2. So this is the pivot element. So I can say that pivot is simply equal to ARR of end, that is the last element of the array. Now what we are going to do next over here is that I will maintain regions. Okay, so now I want to do the partitioning. Okay, so what I will do is first I will take, let's say, a pointer I, which will iterate over all the elements starting from the start till the end. So this is where my start is, and this is where my end is, correct? So I is simply a pointer which is going over all the elements. Next, what I am going to do is I will also maintain a pivot index. So what will pivot index do is, let's say if pivot index is at this position, right, then what does it mean is that all the elements before the pivot index, right, are smaller than 2. I'll repeat it once again. If pivot index variable is at a index I, okay, then it represents that all elements from start to I, okay, are less than the pivot element, correct? And that makes sense also if you want to divide everyone into two groups. Okay, let's say all the people less than height 10 in one place and all the people greater than height 10 in another place. Okay, so if you simply just take all the people less than height 10 in one place, the other part will automatically also have the elements greater than height 10 people, right? So that's what we are going to do. So this is how it will work. Okay, now I will take the element into consideration. Now the 7 element, okay, is going to be greater than pivot element, right? So currently pivot index is here because nothing before this is present, so that means no smaller elements. So in this case, if the element is greater than the pivot element, don't do anything. Simply move to the next element. Now we have minus 2, right? So what will happen over here is this element is less than the pivot element. So simply swap the element at the pivot index and over here. So what will happen is minus 2 will come here and 7 will come here. And then this variable will also get incremented. And it makes sense also. The logic is also correct because all the elements less than the pivot element are on the left side of pivot. Then consider the next element, I is over here. Okay. Now you have 4. 4 is greater than pivot element, don't do anything. Now you have I over here. Now 1 is less than pivot element. So what do you do? Again this swap. So 1 will come over here and 7 will come over here. Okay. And then we increment this pointer as well. And it makes sense also over here. Correct? Because all the elements less than the pivot element are on the left side. Okay. Now next what we are going to do is we are going to consider 6. Now 6 is greater than pivot element, don't do anything. 5. 5 is greater than pivot element, don't do anything. 0. 0 is less than pivot element, so a swap. 0 will come here and 4 will come over here. And the index of the pivot element will be increased. And all the elements less than pivot over here. Now this is minus 4, again less than the pivot element, right? So what we are going to do is we are again going to do the swap operation over here. So with that my minus 4 will be over here and my element will be over here. Alright. Now with this you've done the correct arrangement, right? All the elements less are over here and all the elements greater are over here. Now you just need to bring this element right in over here, Correct? So that is why what you will do is the last swap that you will do will bring 2 over here and it will bring 6 in the end. Okay? So this is what you have to do over here whenever you are doing the operations. You have to do repeatedly the swap method so that the elements are being partitioned the right way. So let's look at this approach also now. So here I will keep a pivot index which is the end of the array, and this is pivot value, okay, pivot, or you can also say, and this is the pivot index which is basically starting from the start. Now you go to all the elements from the start in the array to the end. Okay, so now you will check if ARR of I is less than the pivot value. Okay, so if that is indeed true, you swap the elements. For swapping in JavaScript, we have a simple method: ARR of I, ARR of pivot index is nothing but ARR of pivot index and ARR of I. So that will swap, and also we need to increment the pivot index. Alright. Now once you're done with this, right, once you have done this entire process, you need to bring the pivot element also in the right position, right, just after the elements smaller than the pivot element. So what do you do for that? You again do the swap. So now this time you do the of this and ARR of end, and then you do over here ARR of end, ARR of pivot index. Okay, and then you return the pivot index. Okay, now let's call this function. And see if this works or not. Let me take the input of these elements only. And the end is ARR dot length minus 1, and then you simply do console.log ARR. Let us see. This variable value is not correct, that's why it was giving the error. Pivot, let's call it pivot value only. So there is just some naming issues, and you can see here we have the sorted array. Clear to everyone how this is working? Just very simple partitioning process that we are applying over here to solve this. Correct? So this is how we get the sorted arrangement. Again, very simple. Just keep on applying the partitioning process again and again, and every call to partition, one element at least is going to come at its right position, right? And this is how you have to keep moving forward. So I hope this was helpful for you to understand how this is working. I have implemented the entire code as well for your understanding, so that you can try it out yourself as well and really understand the crux of Quicksort. Okay. So thank you so much for taking a look at this video, and I will see you in the next one. Bye.